this session of the part 1 of the series of lecture. Welcome back. So the topic today will be phase. What is phase? Phase is a very, very common terminology that you encounter everywhere in physics, even in mathematics. So this is usually the phase plot you can see in many disciplines. For example, it tells you the trajectory at different status, and you can consider or take a look at the location or the phase and study the dynamics of the system. And in medicine, there are many examples. For example, you can have this pressure volume plot describing your cardiac function. So you can see this is a time dynamics and time dynamics. And with this phase relationship in between pressure and the volume, we can get a lot of health information. But all these are kind of here and there. Let's take a look at this interesting example from a very simple mathematical model perspective. So on the left-hand side, you see there are 3 morphologies, right? This is circle, this is square, and this is hexagon. And on the right-hand side, you can see 3 different morphologies. And what are they? If you pay attention, you see there is an angle, right? The angle is fixed, but according to the location of where the angle is, you get very different morphology or oscillatory signal on the right-hand side. So what it suggests? It suggests that the phase, the angle, tells you what is the status of the system right now, but this circle can be viewed as the system that is observing the phase. And on the right-hand side, as we have discussed, they have different wave shape function, but the same frequency or the same phase. Okay, so after this very simple example, let's take a look at the traditional approach. So the traditional approach to get phase is via, was proposed, maybe the first one I know was by Gabor back in 1947. They just use Hilbert transform to generate analytic function. And once you get analytic function, then you can take the phase to evaluate, use the phase in the exponential complex domain phase and define the phase to be this featured out and by unwrapping. That's the traditional approach. Suppose you have this guy, analytic function, then you can define phi immediately. Otherwise, you have the real form, then you apply Hilbert transform, or some kind of, you can combine it with continuous Webby transform or bandpass filter, etc., to get the desired phase. Is it a good idea? Maybe not. As we have discussed in the previous session, Hilbert transform may have some limitation if you consider wave shape function. And you can see that the phase is not monotonic. Why? Because of the winding issue. But here, this is 1.01, you cross 0, so you get more winding. So the phase is jumping. So the phase is not unique. Even for these 2 signals, they look so similar, right? So what is good about it? Another example is here. This is the PPG signal, a real-world signal. And as I told you, there are 2 components inside. One is the cardiac component, the high-frequency one. Another one is the respiratory component, the low-frequency one. And that is the phase you get by using the traditional approach. And here, what I plot is, I plot the phase, but I mark by 2 pi so that you can see the detail. And this is an instantaneous frequency, which even has negative frequency, difficult to interpret. And this is a superposition of this instantaneous frequency on the synchro-squeezing transform. So clearly, well, at least it's clear to me, or well, to me it's difficult to interpret what's really going on. What is the phase? I don't know. Another example is the respiratory signal from different sensors. So you have, this is recorded simultaneously from me, I remember. Yeah, you get several different respiratory signals. This is a pressure, this is the flow recorded from nasal cannula. You have entitled CO2, you have impedance. Is this by me? Anyways, I forget. This is a signal, anyways, simultaneously recorded from some subject. Because I remember I don't have entire CO2. Okay, whatever. Okay. But you see, what is the common? The common is the phase is fixed. The phase is fixed. Right? They coincide very well. But the morphology, the wave shape functions are different. So you can see that the phi can now be understood as the internal clock of the breathing cycle or respiratory dynamics, or the time, for example, the timing of inhalation, exhalation, and so on. For this SL, the wave shape function describes the sensor-specific feature of the respiratory dynamics. And if you recall the very simple mathematical model I showed you, the circle, the square, the hexagon, that is kind of the observation of the phase. We can view this as sensors. So now if we apply Hilbert transform on those four signals, but before that we apply some bandpass filter to remove the chain. Then you see the phases of these four signals looks reasonably well, right? They coincide reasonably well. Okay, mathematically it's correct and nice. It seems to make sense. But if you take the derivative to evaluate instantaneous frequency, you see they do not coincide. They do not coincide. This is not physiological. So although it's mathematically correct, but physiologically it is problematic. So our proposal to resolve this issue is the following. Because Hilbert transform cannot or is limited to handle time-varying dynamics, amplitude modulation, frequency modulation, it can handle that kind of signal only under very specific high-frequency carrier situation. But physiologically, we do not have this kind of high-frequency carrier to allow us to achieve the goal by Hilbert transform. So we propose to consider adaptive harmonic model or adaptive non-harmonic model, and we achieve the phase by decomposition. That is, we decompose the signal into each component, and the phase is actually defined as a vector value function. A vector value function. So suppose there are k components inside. These k components may come from different systems. So it's better to decompose them and study their phase separately. So that the phase is actually a vector value function describing different systems. And if you pay attention to this definition, let's take a look at this example. Old and new definition. In the old definition, as you can see, the phase difference in between the true phase, well, it's very weird, and you have seen the difference. But if you use instantaneous synchro squeezing and do the decomposition, and you get phase difference compared with the ground truth, you get the phase accurately back. And this is a quick recall of the reconstruction. You have noisy signal, you get synchro squeezing, and you have bend. You run this bandpass, time-varying bandpass filter for the reconstruction, you get the decomposition. And now if we apply this idea combined with what we have introduced, SAMD, which I will skip because we have introduced it, then you get a decomposition. And for each decomposition, you evaluate the phase of the fundamental component, and you take the derivative, you can see a very well superposition. So you can get two systems. One is cardiac component, one is respiratory component. And once we have the respiratory component and the cardiac component, then we can study even their interaction. For example, cardiopulmonary coupling, that is the topic we will discuss in the next session. And then back to the respiratory signal example. These are the synchro squeezing transform of these 4 signals, and that will be the phase, and that is the instantaneous frequency. You can see the instantaneous frequency fit across different channels, and the value are reasonable, which describes how fast the respiration is in an instantaneous momentary sense.